Of you today here, so thank you for coming. And I hope that quantity of you somehow reflects that interest in new technologies, new and cool technologies, in particular into the database. So my name is Jurģis Orups, and I'm a co-founder and the CTO of a company from Latvia called Clusterpoint. And today I'm going to tell you a story. So this story will contain some experience what we have when we build this new tech company. So this presentation will contain some slides from our everyday, so building the startup, building the new tech company, and also will contain some technical slides. So I hope you enjoy both of them. So let's hit the road. Okay, so this is the funny thing actually. I'm a father of 4-year-old daughter, and yeah, watching grow her, it's actually so many similar to building the new tech company. So when I do this presentation, I will go through all these phases, which is like a funny. So yeah. Starting from idea, which was like planning the baby, then the child was born, and so we started to play with it, and yeah, made the first version. So this is the phase of minimum viable product. Then we have some bruises and scars when we hit the road, and so we have to stand up again and go forward. So went through the trial and error period, and nowadays we think, at least we hope, we are the age of teenagers, so we have enough courage to say some strong words about what we do and stand behind that. So, and as every child wants to be the grown, so do we. And actually, we want to be among those big guys out there, and yeah, show our muscles. But yeah, we need to do some homework. Okay, so the inspiration we have about this NoSQL database technology was dated almost past century. So we worked, the part of our core team worked together in the company which provided the information. So it's like sold information service, sort of business to customer model. And yeah, we have quite a lot of data which we should kind of sell. And more and more we have some unstructured data within. And in that time, that was a quite big pain, and sometimes it's already also nowadays that unstructured database is the pain. So that time that was a huge pain. So yeah, we decided that we need to improve this, and we made the full text search engine for software stack we were using at that company. So we did that, but that was kind of, okay, we did, that was interesting, that was working, but we wanted to do some more. And that time, everybody knew already the Google, but for local market in Latvia, Google wasn't good enough. So we wanted to try to compete with that and made our own local Google and name it Ciets.lv, which perhaps for Estonians or English speaking say nothing, but it's a word in Latvian, which is, when translating, is a sieve. It's like when you are sieving something out, when you get most relevant information out of there. So that was the first our implementation of this full text search engine at the scale. So here is, yeah, I looked a few weeks ago in the cool website which is called webarchive.org, when you can kind of spin like a time machine, when you can look what the page looked like 10 years ago, and I actually find it. So at that time in 2003 we have 2,700,000 web pages crawled, and that was more than a Google that time. So that was yeah, that was our that actually make it fun. And what we did better than Google that time was that we localized the search for Latvian language. So we provided search in word forms. Then we kind of tried to be more deep, make some deep crawling. So we have a bigger index at that time. So that was a great experience building the first scalable and distributed search engine. Okay, so here you see the change in the background. So you will see that kind of slides later on, but when you see this white background, I'm gonna speak about some technical stuff. So anybody who uses full text search and in auditory? Okay, so anybody heard something about the inverted index? Cool. So we have a couple of hands. Okay. So for full text search engines, the basic structure, how the index is built, is inverted index. So from the word of inverted, it already means that there's something vice versa. So, for example, if you have records like web pages, we have lots of text there. So what inverted index effectively do? So it creates the dictionary of all terms present in the data set. And another part of that is the so-called posting list. So, and each posting list contains the documents where this particular word occurs. So, for example, here we see the word Alice, which occurs in document 1, document 2, and document 3. So, and this number actually is the position. So I will talk later on why those positions are crucial for this type of index. Okay, so we have some basics about the inverted index. And yeah, what this index can provide for us. So basically, when we do the full text search, we just do Google-like search on a content. So here we have the same inverted index. And for example, I want to search for documents which contain words Alice and King. So what it effectively do is make the intersection between those two posting lists. So if you have studied some in university algebra course, then this comes from theory of set algebra. So you have like intersection, you have union, and you have complement. So yeah, so basically those operations made possible to make AND operation when you want to search one and another word. If you want to use OR, then you just join those groups together. And in this example, so we have a word Alice and the King, and we want to make intersection between those two sets. So it's actually document 1 and document 2. Okay, are you with me? Okay, cool, great. Yes, let's get back to the storyline. Okay, in 2006 we established the company. So I think that we were the first startup in Latvia. So we attracted the first seed fund there, and yeah, we have two and a half developers. Actually, we have three, but yeah, almost all of us was developers. Yeah, there was a crazy time when we code this first version of our product, and we didn't forget to buy the Google again. So we thought that if previously we somehow succeed with competing with Google, so why don't we try it again? So that was a crazy idea, and it turned out that didn't went so well, but we had a good feedback from our customers, which said, well, yeah, search appliance maybe is not the best product we need, but if you could provide some similar approach how to manage the data, that would be great. And that was the first turning point of our company, that we saw that there should be something there. We need to think the new way of how to manage the data. Okay, let's get back to index. So at that time, full-text search engines worked like you just get the whole data from the database and put into full-text search engine. So there was no possibility to change the data. So if you have some updates in SQL, you have to load the whole data again and kind of provide this search only on the snapshot of the database. So that was a sort of pain for developers, or that kind of restricted functionality of your applications. So at that time we decided there should be some solution for that. So what we did, okay, I will just add why this is actually the problem. The problem is that when we put the new documents to the index, we store those posting lists actually at that time on the disk. So to make this thing optimal, we have to store those posting lists into sequentially. So what it means that it's quite hard to merge some new stuff here or append, because all this data comes in sequence. That's why it's very hard to modify that kind of index. So we decided that we could solve it, and actually this approach was quite successful. So what we did, so we made two types of indexes, those two types of inverted index. One is like memory index, which is mutable, which means you can easily add something to it. And then we have disk-based index, which kind of is similar to what I showed in previous slides. So the idea is that the new documents coming into the database, what we do, we make this mutable index. We put this index into the memory. It's like a buffer. So when the buffer fills up, we dump this buffer to the disk. So at the time goes on, you have a lot of those dumps, and it is quite inefficient to make some retrieval, for example, 100 or 500 files at once if you want to make the search query. So time to time, what we do, we merge those dumpings together, and it makes this index more optimal, and the problem was solved. We have the real-time updates. That was quite good achievement at that time, and we were some of search engine that time that provided that feature. Okay, so then we have a full-text searching. We have a good full-text search. So then we have to think about the query language. Which is the next thing to the database. At that time, JSON wasn't so popular as it is now, so that's why we chose the serialization of documents as serialize it as XML documents. And our idea was to make the query language as much as possible similar to how we store the data. So, for example, if we have like a document which contains CVs, then we have a field like sex, salary, or place. This is like a real XML document. So the query would be very similar. So we just say that we want to find all females within the salary range placed in Dublin. That's it. So this is the query language. So also we wanted to make it very, very simple. We also provide some simple query capability. So this first query is valid query to the database. You just say what you want, like you do in the Google, and database will search for it. And that's not the last thing. As a normal database, the one thing is to filtering the data, but after some time you want to make some reports or charts or graphs, so you have to make some aggregation in. So we thought about also aggregation language, but we didn't come with some better language than SQL. So we mixed those things, two things together, and this is a way how you make aggregation into Clusterpoint. Okay, speaking about aggregation, to speed up the aggregation and to be kind of very, very fast what we do, we created a new type of data storage, and we called it the lookup tables. So actually the lookup tables is columnar type index, and it's very effective when you need to scan whole column of data. For example, if you need to make some summing up one column, so it's easy just to scan it and sum those values. So the best of this data structure is that it's accessible in constant time and modified time. So it's memory mapped. We haven't to manage how to persist the data. So operating system keep it for us. Yeah, and it's very good when you do the aggregation, faceting, and filtering. Okay, good. So yeah, we had full text search, we have some aggregation, we have query language, so we thought that we are good to go to the market. So at that time, we have a trust in enterprise sales model. So we reach out our local customers and did very, very good with them. So we have a couple of business directories, portals, e-shops, some projects in public sector which required that kind of functionality. However, positioning as a database at that time was quite challenging, because at that time no one knew about the NoSQL. There was like just a relational databases, and then when we go to the customer and say there's a database, then they ask, oh, where's the relations, where's transactions, or oh no, it's not a database. And actually, we also haven't heard anything about the NoSQL, but later on 2008, 2009, there was like a meetup where this NoSQL idea was born, and yeah, we thought maybe we are the NoSQL. Then we tried to check, put the checks. Are we there? Are we there? Are we there? Yeah, we are there. Oh, we are the NoSQL database. That was kind of a surprise for us that we developed technology which turned out after a few years, this is the NoSQL database. So that was kind of encouraging for us to keep going and yeah, improve. So yeah, and here is our friendly family of all NoSQL market. Maybe not all the players are present there, but most of them. So as you know, there is NoSQL market is split in at least 4 categories. So we have document-oriented database where we store the data as documents. We have graph databases to process graph information, graph type of data, wide column stores, key value database. So Clusterpoint is at a document database field. And this slide is very important for investors. They really like it, because when we show that yeah, in 2011 the market share was quite smallish, then the projection, what analyst says, is quite great. So that's why we love this this graph as well. Okay, so let's get to days where we are now, and actually making this direct sales or enterprise sales, we learn a lot of it, but it's quite tough to do that. It's very expensive, and also we wanted to be more open of what we do, and we tried. So we put less trust in enterprise model for such technology as NoSQL database. So we make a shift to free software and more on the cloud. So and our current goals is to grow customer base, keep innovating, and actually develop this software for developers, because I'm also a developer, and I want to make this database very convenient to use, and that's the trick. Okay, so speaking about innovations, as you have heard, there is quite a lot of buzz in NoSQL marking speaking about transactions. Anybody here use transaction when developing your applications? Wow, that's great. So I assume you have some time and you thought about how to do transactions on other NoSQL database, and this is quite challenging task to do, but at least yeah. For what reasons? So normally transactions are somehow like related to real financial transactions when I subtract something from one account to another account, but actually the use case of transaction is more wider than that. So let's say we have ATM cash withdrawal process where we have transactions where we put the card, check the PIN, check if we have enough money to get out, then this kind of thing which gives out the money kind of commits that it gave out the money, then you have to kind of check it in the system. So it's like one transaction. Or making some eShop checkout procedure. So you have also have to use those transactions and any other stuff. So yeah, and a year and a half ago, we sit on the table, get some encourage, and thought, okay, we will solve it. So actually, no one solved that problem previously, but we thought that we have enough knowledge to do that. So yeah, speaking of transactions, this is a high-level view on that. So we begin transaction as we do in SQL, just issuing the command begin transaction, then we retrieve the value for, let's say, account number 1, then we retrieve value for account number 2, check some constraints on those values, update value 1, update value 2, and commit. This is the way how we simplified way how we work with the transactions. And how it's done behind the scenes. What we do in our database, when we begin transaction, we fix the view of the world, because it's necessary to fix that, because you want to make those transactions work like in separate space. So that's called isolation. So for that reason, we keep versions for each account. So you can imagine that you have version control where you have like a global revision number for your code. So we do the similarly in our database, in the distributed database, where we have like a global version of the database. It's like a snapshot of the database. This is state. So when we begin transaction, we fix the state of the whole database. So we retrieve value from account number 1 at the state we fixed when we started transaction, retrieve the A2 and check the version of account number 2 value, check also this integrity checks, and we update document only if the version where we retrieve the document and we update document hasn't changed. Otherwise, we roll back the transaction and continue. So similarly, the whole transaction commits only at the time when we have safe updates on both account values, and we save the final version in transaction log. Yep.
So does it mean that while you execute checks and stuff, then at that given moment the database is not accessible and all the other queries to database are in queue and cannot be executed.
Yep. You can execute because we have this isolation level for transaction which is not the serializable, which is the highest level of isolation, but one level below. And that effectively means that if you fix the view of the world, any other queries can run. So any other queries won't see those changes made in this transaction. So there is not the global lock on the database when you do the transaction.
You only lock the values.
Yeah, actually, we use this optimistic locking to improve this concurrency. And by doing that, we actually try to acquire locks only when we do update. So it means when we retrieve the data, we do not lock anything. And we acquire lock only at the time when we are doing update, and we lock just those kind of 2 accounts where we do this update. So that's why you are not blocking other queries or even other transactions. So you can run 2 or 5 simultaneous transactions.
As they do not interfere.
Yeah, do not interfere. If they interfere, so there is a trick. So this check value 1, version 1 is not equal with delta. So I mean, if you check this value 1 in transaction 1, not a value but version 1, and some other transaction changes this account value to version like 3, then this check will be false and the whole transaction will fail because some other transaction change this value in a kind of in parallel transaction.
Okay, thank you.
Yep. Okay, so this is quite straightforward when you do it in single server. So there's no problem. It's already solved. Mostly all of SQL database already does it. But when you have distributed database where one value can be on the one server, another account could be on another server, so we have shards, we have replicas. To make this whole thing work together is quite challenging. And actually, to show how it works behind the scenes, it's like a 2-hour talk about just about the transactions. So maybe some other time we will join DEVCLUB in Estonia to tell how we do exactly transactions in distributed environment. That would be, I think, a good talk. Good. So yeah, why transactions and distributed transactions are tough because of, as I said, of sharding and replication. So you have split the data among the lots of nodes, you have replication, and as you have the large clusters, so nodes may crash and come back. You have to synchronize that thing together. It's quite challenging. For keeping those transactions, we keep the transaction log. So it's like a single transaction log for, I don't know, your account or your database. So in the first view, it's like we feel like, okay, it's like a single point of failure. But actually, the transaction log where all the transactions with the versions are registered are also sharded and replicated. So we made these transactions scale. So it means, when you add new shards, you can scale also these transactions. Yeah, as I said, for high concurrency, we use optimistic locking, but of course you can do like other way around when you acquire lock when you read the data. So as I said before, we acquire lock when we update the data. So another way is to log the data when you read the data. So it's also possible. Yeah, and isolation level we have is repeatable reads. The highest level is serializable. We do support those repeatable reads, which means in one transaction, when you repeat the reads, they will be consistent. So if you in your transaction, initiate the read operation to read some data, then check something, repeat the read, you will get the same results because we fix the view of the world when we start transaction. That's why we have quite strong isolation level on our database. Okay, so here is the code of how the transactions are done in Clusterpoint. So nothing complicated. So we create a connection, create the operation. We just insert initial values, begin transaction, retrieve the values for account 1 or account 2. Change the balance, adding 5, minusing 5, updating those documents, checking again, commit transaction. That's the way how API works with transaction, in that case in PHP. So we have libraries also for other programming language like Java, .NET, Node.js, and we also have REST API to do this thing. Okay, so the database, so it means also some benchmarks, how it perform. So these are tests on a single shard. So and this scalability we have is almost linear. Okay, it's a sublinear, but the trend is linear, not like going that. Yeah. So when we ingest the structured data, which means we have a couple of fields, we can get around 25,000 operations per second per shard. So if you want to get some 100,000 operations per second, it will take you 4 shards, for example. Also, if you ingest some unstructured data, so we have some textual part of data which we have to make this inverted index, which is more complex. So we need to tokenize the data, and we need to make this inverted index. So it takes some time. So we can get some 1,800 operations per second. So we have full text search queries, which are kind of also, but like a worst case, because full text search is more complicated, like ordinary query when we do the range scan or filter something. Yeah, and then we also, here is a number about transactions. So we can get 3,500 transactions per second, which contains 2 reads and 2 writes. So this is current benchmark, but we are improving in all parts. So those numbers might increase. Yep.
How do transaction count is calculated, given that they do not interfere often or interfere randomly?
Randomly. This is when it's random.
Okay.
So,
Yep.
question, what's the underlying code?
For this test? Okay. This one was done on Xeon processor. I think that was Ivy Bridge, like 3.5 gigahertz, 16 gigabytes of RAM, and SSD disk. Yep.
So nowadays, lots of NoSQL database support transactions.
Okay.
And do you have any comparison chart with NoSQL databases or comparing to Oracle, who does transactions for years and hours?
Yep.
So it's not impressive without comparison.
Okay. Yeah. So the thing is about the scalability. So
Oracle has racks with replications. Cassandra has these transactions and scalability stuff again. So. Again.
Yeah, so I think for Oracle, they do a great job. But I mean, if you have the application where you have to scale like I don't know, millions or even billions of records, and you need to run the transaction. So for SQL, it's a problem to make the sharding. So to shard the data, to use this scale out ability of the system. Yeah, but how do you make the join then on partitions, and what's the performance to making joins in distributed partitions?
We have racks, and it works very smoothly.
Okay, great. According to other NoSQL vendors, so when you say about Cassandra, I assume that they say that there are transactions on single updates, so they don't provide multi-document transactions. So what they say that they are consistent when you change each one document. That will be like an atomic operation, and will follow those ACID compliant rules. And this one is a bit different because we do multi-document or multi-record transactions. So there is lots of kind of marketing tricks how they present this transactionality in their systems. So actually, there's not so many out there who supports transactions in distributed environment when you have the sharding and replication. Okay. Okay. So in previous slides, I mentioned that we have the new shift in company to be more open, to be free, and to move towards the cloud, because our colleague from Google also talked a lot of cloud, and we see some opportunity there as well. So the new solution that we are providing is a database as a service. So there is quite a challenging task for us to make this cloud up and running. So currently we have the cloud with 80 CPU cores, 25 terabytes of storage, 3 terabytes of RAM. And the big difference for our offering is that we really provide on-demand resources. So you don't need to provision anything. You just want those resources and you get them. So for example, you have a database, you have some workloads, so you have some spike. You don't need even to provision or say to cloud, I want more. So you will get this right away. And my colleague Petrus will talk more about this, but we use this pay-per-use model, which means when you use this on-demand resource, you just pay for what you actually use. Okay, here is a picture of some racks in a data center. So some wiring stuff, some hardware stuff. So that was fun to make that. So we enjoyed some. And tried to make some art out of that. So that was great time. Yeah, and actually how this cloud works is like we have our software on the hardware. So we split your data among the tens or hundreds of servers. So we shard them, we replicate them. You don't need to care about that. You just make application and work with the database. You don't need to configure, not to care about replication, failover, whatever. So you have the endpoint and you just feed the data into that. Okay, and I encourage you to try it. So you can sign up for a free cloud account at cloud.clusterpoint.com. We have free of charge 10 gigabyte of storage space there for you. And be part of a community, and that's always to have fun. Okay, then that's all for me. I think I can answer questions afterwards, but now I am giving the stage to Petrus. Sure.
So if you have any questions while we change this microphone, because I'm going to talk a little bit different stuff.
So you have your own data center, yes? Not yet. So we are using Telia Sonera in Riga days. So actually, on these days we are opening also our cloud part in US. So yeah, we'll open another kind of cloud like regions in Europe as well.
But does it also mean that, say, your database is disconnected from application, and when you have latency, your stuff always problems when your database is somewhere in Riga, an application somewhere in Amazon, and it's...
So we tend, so our idea is to kind of expand our reach by placing our clouds towards those regions where your application is hosted. So, okay, we want to make our cloud presence in every city, yeah. But I think we will cover mostly all important regions.
What are the reasons to use your solution instead of AWS or Google?
Okay, so
Except for price, you mentioned
yeah,
price.
one is the price. Another one is that this database combines actually two things or three things together. So you have a NoSQL database where you can kind of store the data. You have full text search engine integrated that. And the third part is this callability. So you can easily scale this database. You don't need to worry about scaling it up. So you have just a database which runs fast, it scales, and provides this full text search and all other capabilities which I didn't kind of show.
So you mean you are unique in those three things? Nobody does that except for you?
It won't be true, yeah, but I think we do better than others. I mean, this is a longer discussion about the bits and pieces for every NoSQL out there. Yeah, but we think that our approach to make mixing kind of processing structured and unstructured data together, there is some power.
And then the question, so what is your biggest current, let's say, customer?
Okay, so...
Because for Cassandra, it's одноклассники, of course.
Yeah.
It's huge.
Okay. Yeah, so, yeah, so we have a couple of customers in Latvia, which is maybe not so big, but we have installation when we have like a couple of billions of records in the database. So we have also some tool for log management. So we use also our database for log management, where we need to store lots of data, which is machine generated, to make some nice graphs and charts. We have to make aggregation of that. So we have some experience on a huger scale. Yeah, but maybe there is not so many big customers to name that will kind of tell something about that. So that's our goal, to reach out to get to that.
Okay. So then I'll touch another topic, and it's probably going to be something related to your question about why to use at all our cloud, and what our technology allows us else do, and what we think that we can challenge the way cloud computing is done today. So that this is a bit different way we look at the cloud computing. And how we do that, it has been talked about already. It's about instant scaling, and instant scaling is really when you get your resources exactly at the moment when you need it, so that you don't need to provision it up front. But when you have a spike in performance, you get the resources instantly. And again, talking about the pricing, it's a bit different way of pricing that scaling. And let me give you an example of the cloud computing today. That's first of all, what you have to do is predict your future needs for hardware. So you know approximately how much computing power you would need, and then you provision it. you make a kind of an assumption and also make a secure overhead. So in case there is a spike, you don't stop, your solution doesn't stop or slow down. And then you pay for it. Either you use full capacity or you don't use the full capacity. And the thing that you can't scale instantly, which I already told you. And here's the example. Let's say if you have provisioned this red part, and you also pay for this. Either you use, you don't use, you pay for it. But then your real need or real usage is this blue part. And you see there is a difference in that. And here comes the performance issue when your application may slow down because you don't have enough resources. And this basically what we say, this is a kind of a waste of money, because what we want to do, yeah, sorry.
What about auto scaling? It's like it's quite usual to use auto scaling cloud. It doesn't look like cloud to me.
No, but it's about provisioning your hardware, right? You usually book, let's say, 4 CPUs or 4 cores for your application, and you pay for those cores. And it comes also with all the computing power. It's a memory, or this is, let's say, RAM. So you provision something and you pay for it. But not necessarily that at each point of time you need all of this. I'm sorry, it's not working. It's not necessarily you need all this all the time. And there is this difference, which you kind of overpay. Does that answer your question? Or?
Yeah, but why wouldn't you use just smaller nodes, like smaller capacity nodes, and then spin as much as you need to follow this graph?
You mean like with upscaling, downscaling?
So actually, so it's not like a containers when you have something that you have already there. So we have the resources, you have your database. So if your database requires lots of like CPU time or disk, you can get that. So you don't need to think about that if I have that problem, so in the application I need to issue API which kind of over-provision, not to over-provision, but increase my resources on the cloud. So by that meaning also we also balance those resources among those servers, so we keep them balanced. So in case someone needs some resources, we can get them and give them to you.
So let's assume one of the customers gets hit by a massive DDoS.
Yeah.
What happens? How
So-
do you limit the impact?
Yeah, so I mean, if it's like a DOS, then I think there should be some prevention to kind of solve this issue about the DOS. I mean, it's not in level like a database in the cloud that would be like a special device which will handle those DOS attacks and kind of solve this issue. But I mean, I think the question was about if there is like a DOS attack, so my expenditure goes north, right? That doesn't.
Also, you might be that the bigger DDoS might overwhelm the cluster. You have a limited set of hardware, and a massive DDoS might be able very well to utilize fully.
Yeah. Yeah, sure. So yeah, our cluster will monitor this pattern of kind of growing kind of requests per second, or is it like if it's like TCP flow, then there's a specific device which will handle this the thing. So we need to kind of separate legitimate traffic from like DOS attacks. So if it's a legitimate traffic coming in, so and it turns out that there is kind of out of resources in the cloud, then yeah, this is a problem. And of course we will kind of poll or throttle that particular customer, and we'll keep it kind of lower some records per second and stuff like that. So yeah, this is kind of extreme situation, and there are solutions to fight with that. But I think yeah, this pricing issue can be the problem if you have kind of legitimate traffic coming in and you haven't predicted that, so then there is also possibilities in our cloud how we can deal with that.
Okay. So the essence of cloud computing is really when you really use the power of cloud. So the resources which are in the cloud, you use those resources rather than having your own machines and running the software on your own end. That's the essence of the cloud. And this is how also Clusterpoint database is built to use those massive resources which are there in the cloud, because it's distributed among all those servers, and whatever the request comes, it either uses part of the cloud or it uses the whole cloud to answer your requests towards the to answer your requests. Yeah. So this is actually, I hope you got a clearer understanding how our software is built and how it is put in the cloud and what is exactly our offer in the cloud. Currently, you can sign up, like you just said, and it's free of charge. We don't charge anything yet, and you can use as much resources as you need at the moment. It's going to take a couple of weeks or months when we introduce also pricing. Any questions?
Question: Have you thought of moving not to hardware but to some cloud resource like platform as a service or something like that? So that would save you from that spike.
Yeah. So you're kind of proposing that we could use some existing already infrastructure as a service, like Amazon or
like buy from Google for special price because you're big.
So yeah, it's possible actually, because we run this cloud on a bare bones. So if we can get the dedicated hardware in the Google or Amazon or Lexbase or whatever, so we can run it. So that's also the I tried to answer the question about about those. For example, if I have like an application on Amazon, what the latencies and stuff. So if we kind of make our one of the clusters there in Amazon as well in regions, so we can solve this latency problem and get kind of both best out of it. Okay.
That's all, I think. I think the first